In this video, we're going to be looking at the first of a list of tests, and the first test is going to be the nth term divergence test. And really, we're going to start off here by sort of asking a question, and that question is, what can the limit of an, the limit as n goes to infinity, tell us about the behavior of the infinite series? So what can this limit tell us about what happens if you add up that infinite set of numbers? Okay, so here the first thing is that if we have a convergent series, so if an is convergent, then it must be that the limit as n goes to infinity of the terms being added up, that limit has to be equal to 0. In other words, in order for this series to actually just get infinitely close to some number, in order for it to not increase without bound, it must be that the terms being added up get infinitely small as n goes to infinity. In other words, if these terms here don't get infinitely small, then there's no way for this series to be convergent. Okay, so this is the first statement that we have, and it should make some sense to you when you first hear it, but what we're going to do is actually prove it. And this proof gets a little bit technical, okay, but our goal is to prove that anytime we have a convergent series, it must be that the limit of the terms being added up goes to 0. So let's take a look at that proof. So first off, we're going to be assuming that our series is convergent. And what we're going to be showing is that the limit as n goes to infinity of the terms being added up, that limit has to be 0. Okay, so here at the start, we're going to sort of define a couple things. We're going to state a couple things. And the first thing is that if our series is convergent, okay, then that means it actually is equal to some value. So here, our series, let's suppose that it is equal to s. Okay, if it converges, let's suppose that it converges to s. And that means that the limit of our partial sums as n goes to infinity, that has to also be equal to s, because these two things right here have to be equal to each other. Okay, and that also means that if the limit as n goes to infinity of s sub n is equal to s, it also means that the limit as n goes to infinity, s sub n minus 1 is equal to s. Now, why we're looking at this partial sum here specifically is probably not going to be clear, but you will see in a moment why we care about it. But if you think about the way that limits work, all that this is going to be here, this is the sum of the first capital N terms. Well, this is going to be the sum of the first capital N minus 1 terms. And as the number of terms capital N goes to infinity, both of them are going to have the same limit. Both of them are going to behave in the same way. They're going to just approach that value of s. Okay, so we have that both of those values are the same. So now let's see how that helps us. So here, if s sub n is a1 plus a2 plus a3, and so on, the second last term would be a sub n minus 1, and the very last term would be a sub n. And now let's take a look also at s sub n minus 1. So it's just going to have one fewer term. It's not going to have this very last term. It's just going to stop at a sub n minus 1. If we look at the difference between these two, so let's take the s sub n and let's subtract s sub n minus 1. Well, what's going to be the difference between them? We will notice here that if I'm doing this one minus this one, it's going to be here a1 minus a1. Those are going to cancel each other out. And we have a2 minus a2, a3 minus a3. All of these terms are going to cancel each other out, including a sub n minus 1. This is the only term that will not be canceled out, and so we end up that the difference between these two is going to be a sub n. Okay, so here we just want to stop for a second. Let's remember what we're trying to do. We want to show that these terms, a sub n, okay, these are the terms being added up in our series. We want to show that they get infinitely small, that their limit is 0 as their counter goes to infinity. So let's just check. Let's take the limit. Okay, let's do the limit as the number of terms here, or let's take a limit as the value n, our counter, goes to infinity, and let's do the limit of a sub n. Well, we know that a sub n is equal to s sub n minus s sub n minus 1. So that means we have really the limit as n goes to infinity, s sub n minus s sub n minus 1. And now I want you to take a minute. I want you to think about how this proof is going to end off, because we are pretty much done here. What happens with these terms as capital N goes to infinity? So pause it for a second and make sure you can finish off. Where's this going? And what we get is that here, s sub n, that's going to be going to s. And s sub n minus 1, that's also going to be approaching s. So what we end up with is s minus s, we end up with 0. And that's exactly what we wanted to show here. We needed to show that our terms being added up, okay, the actual terms being added up, that they have to get infinitely small if our series originally was convergent. Okay, so that's the proof there of this statement, is that if our series is convergent, it must be that the limit of an approaches 0. So this is what we have just proven. Anytime we have here a convergent series, it must be that the terms being added up get infinitely small. And this is going to be the basis for the nth term test for divergence. So now let's actually state what that test is going to be. So the nth term test for divergence, sometimes it's just called the nth term test, or sometimes just the test for divergence. And what it says is, what if the limit as n approaches infinity of a sub n? So what if the terms being added up don't go to 0? Okay, so first off, if the limit of these terms is not 0, okay, it means the terms being added up don't get infinitely small. And if you keep adding up an infinite number of terms, and those terms are not getting infinitely small, then this sum right here is definitely not going to be convergent. Okay, so the nth term test for divergence says that if this limit is not 0, or if it's DNE, so maybe if those terms, oscillate back and forth, they're sort of jumping back and forth between, positive numbers and negative numbers and so on. If they're jumping all around, it says that if either one of these things happen, then it must be that your series is going to be divergent. Okay, so here we know that if it converges, that limit must be 0, and now we're saying, in other words, that if the limit is not 0, it must be that that series is going to diverge. Okay, so this is going to be the nth term test, and really moving forward, it's the first of many tests that we're going to learn, and it's going to always be the easiest one to apply. Okay, and it should always be the first one that you look at whenever you are looking and testing a new series. Okay, the first time you see a series, take these terms being added up, do the limit quickly. Sometimes you can do it in your head. You don't even need to write anything down, and see what happens with that limit as n approaches infinity. So let's take a look at an example. If we have the series from 1 to infinity of n squared over 5n squared plus 1. What we want to do, if we're going to use the nth term test for divergence, we're going to check right away the limit as n goes to infinity of n squared over 5n squared plus 1. And this one, you're going to get infinity divided by infinity. You could use L'Hopital's rule. You could look at the degrees here, n squared over n squared. You will end up getting that this limit is 1 over 5. And so if that limit is not going to be 0, then right away we know this is going to be divergent, and it's going to be divergent by the nth term test. Okay, so that's very much how we would look at a question like this. And if the nth term test works, okay, if that limit is non-zero, then you're done. It's actually a very straightforward question when the nth term test works. Okay, so when I say that, all right, obviously I'm implying that sometimes the nth term test does not work. Okay, so let's take a look actually at this question. And the question is, if the limit as n goes to infinity of a sub n, if that limit is 0, what happens? So if that limit is 0, does the series have to converge? Okay, we know if it's not 0 that it's divergent. So if it is 0, does the series need to converge? Let's look at a few different series. Okay, so let's suppose we have 1 over n squared, and if I have 1 over n. Okay, so both of these terms, okay, if I were to do the limit, if I were to do the nth term test on them, both of them have terms that go to 0 as n approaches infinity. Okay, however, what we will see very soon as we've looked at the integral test, is that one of these is going to be convergent. Okay, the first one here actually is going to be convergent, but the second one is going to be divergent. Okay, so really what that means is that even if the limit here, even if the terms being added up go to 0, that is not enough to guarantee that your series has to converge. Okay, and this is very much in line with what we saw when we were doing improper integrals. Even though the height of the function, okay, goes to 0, we ended up with some integrals that converged as x went to infinity and some integrals that diverged as x goes to infinity. And in this case, we're looking at the same thing. It comes down to how quickly these terms go to 0. Okay, do they go to 0 fast enough to ensure convergence? Or are they going to 0 slow enough that this sum continues to grow without bound, causing it to be divergent? Okay, that's very much the idea here. So let's just sort of summarize that for this first one. This one converges, and we have that the limit as n goes to infinity of an, which is 1 over n squared, that's 0. However, the second one, this one diverges and also has a limit as n goes to infinity of the terms being added up that is 0. Okay, so our answer essentially has to be no. Okay, so therefore, no. Okay, if the limit as n goes to infinity of a sub n is equal to 0, then we cannot conclude that the series converges. In fact, if the limit is 0, that's going to happen a lot, first of all, but it also means that the test fails. The test is inconclusive. So if the limit is 0, then the test is inconclusive. Okay, in other words, you're going to have to go do something else, and very likely that means you're going to have to go and use a different test. Okay, so our test is inconclusive if that limit is 0.